Hawking was right. In 1971, from a wheelchair at Cambridge, he wrote down a claim about black holes that most physicists assumed would stay a claim forever. 50 years later, the universe just checked his math. But this isn't a story about a genius finally getting his flowers. Between the moment he wrote it and the moment anyone could prove it, 5 decades passed. Hawking died in 2018. He never found out. So what exactly did he get right? And what's the one idea, the strangest, most important one, that's still sitting unproven? You're watching Infomix. Join me today as we trace 50 years of black hole physics, from an idea too strange to test to the exact moment reality caught up with it. And the biggest piece of the puzzle, the one that could rewrite everything we think we know about black holes, still hasn't been solved. For most of the 20th century, black holes were treated less like real objects and more like a mathematical inconvenience, a place where Einstein's equations broke down and physicists simply stopped asking questions. Then, in 1971, a 29-year-old Stephen Hawking published a short, strange paper. His claim? The surface area of a black hole's event horizon can never shrink. It can only grow, or at best stay the same, whether matter falls in or two black holes collide and merge into one. It became known as Hawking's area theorem, and it sat completely unconfirmed for over 50 years because the technology needed to test it, reading the faint fingerprint of a black hole from a billion light years away, simply didn't exist yet. By the end of this video, you'll understand exactly how physicists finally tested an idea that had been considered untestable for half a century. And you'll understand why, when that confirmation finally came, it felt less like a triumph and more like the universe closing a loop that Hawking himself never got to close. But to understand why this took 50 years, we have to go back to the year the idea got stuck. In 1971, Stephen Hawking made a claim about black holes so strange that even he wasn't certain anyone would ever be able to test it. His area theorem stated that a black hole's event horizon, the boundary past which nothing, not even light, can escape, behaves like a ledger that only ever adds, never subtracts. Throw matter in and the horizon grows. Merge two black holes into one and the resulting horizon has to be at least as large as the two originals combined. It can shrink for no one, under no circumstances. What made this fascinating to physicists wasn't just the claim itself, it was where it came from. Hawking didn't observe this by watching a bunch of black holes and noticing a pattern. He derived it purely from the math of general relativity, applied to an object nobody could see directly, sitting in complete darkness, potentially billions of light years away. And that was exactly the problem. If no one could look inside a black hole, or even clearly see its edge, how would anyone ever check whether the math was actually true? For most of the next 4 decades, testing Hawking's theorem seemed like a closed door. The first real crack came in 2015, when the LIGO Observatory made history by detecting gravitational waves for the very first time. Tiny ripples in the fabric of space-time, released when two black holes spiraled into each other and merged. Think of it like trying to determine the exact size and shape of a bell from a single, faint clang picked up half a mile away. That's roughly the challenge LIGO faced with that first signal. It proved gravitational waves were real. It did not have the precision to test something as exact as horizon area. In 2021, a team of researchers tried anyway, going back to that original 2015 data and attempting to measure the black hole's horizon before and after the merger. Their result? 97% confidence that the area had grown, just as Hawking predicted. For a moment, it looked like the case might be closed. But 97% isn't proof. In physics, a probably isn't the same as a yes, and skeptics pointed out that the original signal was simply too faint and noisy to fully rule out error. The math hadn't shrunk, but neither had the doubt. What the community actually needed wasn't a cleverer argument, it was a louder black hole. So if the 2015 data couldn't settle it, what would it take? The answer arrived a decade later. On September 14, 2025, 10 years to the day after that first ever detection, LIGO researchers announced they'd caught something new, a signal cataloged as GW250114, described as the loudest gravitational wave event ever recorded. Not a whisper this time, closer to a shout. Researchers measured the combined surface area of the merged black hole's event horizon and compared it to the two original horizons added together before the collision. The result matched Hawking's math with far greater precision than anything before it. The area had grown, exactly as his 1971 theorem demanded. And just days before this video was made, scientists released the largest catalog of gravitational wave detections ever assembled. 390 confirmed black hole mergers in total, adding even more precision to the same result. What had been a single, contested measurement became a repeatable pattern, checked across hundreds of collisions. The theorem held. And that changed what a black hole actually is, at least on paper. Confirming the area theorem doesn't just settle an old argument. It forces physicists to treat black holes as something stranger than a cosmic drain, as genuine thermodynamic objects. Back in the 1970s, Hawking argued that a black hole's horizon area behaves exactly like entropy, the same quantity that always increases in a cooling cup of coffee or a shuffled deck of cards or any closed system in the universe. Think of a black hole less like a bottomless pit and more like a furnace that can never cool below a certain point. It can only grow hotter or hold steady. This is why physicists now say black holes have a temperature and obey their own version of the laws of thermodynamics. Confirming the area theorem doesn't just support one obscure equation, it validates the entire framework underneath it. But that framework has a problem. The old model of a black hole was simple. Things fall in, nothing ever comes out, end of story. But if a horizon obeys the same laws as heat and entropy, the same laws that govern everything else in the universe, then something, somewhere, has to be able to move, maybe even leak. The nothing ever escapes model doesn't survive contact with thermodynamics, and that crack in the old picture is exactly what led Hawking to his other, far stranger idea, the one that still hasn't been proven. Hawking's most famous claim about black holes isn't the area theorem. It's the one that came 3 years later in 1974, and it remains unconfirmed to this day. Building on that same thermodynamic logic, Hawking proposed that quantum effects at the very edge of a black hole should let a faint stream of particles slowly escape, now known as Hawking radiation. Picture something like a nearly invisible mist rising off a container that was supposed to be completely sealed. If Hawking radiation is real, it means black holes aren't eternal. They slowly lose mass over unimaginable timescales and eventually evaporate. It may also solve one of the deepest problems in physics, the information paradox, the question of where all the information about everything that ever fell into a black hole actually goes. As recently as 2026, researchers at Penn State have already begun extending Hawking's original equations to black holes that aren't calm and steady, ones that are actively forming, merging, and possibly evaporating in real time. It's exactly the kind of groundwork that could eventually lead to catching this radiation directly. Here's where things stand. Hawking's area theorem, once dismissed as an elegant but permanently untestable idea, has now been confirmed to extraordinary precision, using signals from black hole collisions over 1 billion light-years away. That confirmation came from the LIGO-Virgo-KAGRA collaboration, cemented by the newly released GWTC5 catalog in July of 2026. But the real significance isn't the theorem itself, it's what it says about how long it can take reality to catch up with imagination, and what it means that the man who bet 50 years of his working life on that math never got to see the final grade. There are still questions this doesn't answer. Does Hawking radiation actually exist? Does it truly carry information back out of a dying black hole, solving a paradox that's haunted physics for half a century? These aren't small gaps. They may be the difference between a black hole as a vault that keeps everything forever and a black hole as something closer to a recycling system for the universe itself. Hawking spent the back half of his career betting on math that nobody alive could check. The universe is only now getting around to grading his work. And so far, the score reads correct far more often than not. The next test, the one that could prove his strangest idea of all, might already be within reach of the very next generation of detectors. Thank you for spending this much time thinking about something this strange with me. If you've been enjoying videos like this one, the best thing you can do is hit subscribe. It's free, and it's genuinely what keeps a channel like this able to keep making them.